Hi everyone, welcome to section 9.8 and transformations of functions. So when we transform functions, we're talking about changes that either move them vertically, horizontally, we can stretch or shrink functions, and we can reflect functions. So I know we've explored these before dealing with, let's say, absolute value functions, but we're going to talk about transformations on functions in general. So in order to discuss this or to summarize this, we're going to start with a basic function that we call f of x. So y equals f of x could represent a function that might be a quadratic function. Maybe this is a linear function. Maybe this is an absolute value function or a square root function. So if we can imagine that y equals f of x is just a basic common function, then we can sort of explore how we generally manipulate those kinds of functions. So what you're going to find is that this is a little bit of review, and we'll incorporate some new types of examples as we explore this topic a little bit further. So in the first transformation that we want to look at more closely, we're talking about y equals f of x plus k. So if you could imagine that I'm using a regular function, let's say x squared, if I leave that x alone and I now have y equals x squared plus, so you preserve that function f of x and we add something to it, let's say. So let's say we were to add 7. Because f of x has been preserved, but we're adding 7 to the end or tacking on that plus 7 at the end of the function, this indicates a vertical change. And in the explanation we're given, what we say is if that k value, and we call it a k value, if that k value is something that is greater than 0, we're going to be moving upwards. If that k value is less than 0, we're going to be moving downwards. So if I were to compare y equals x squared with y equals x squared plus 7, that plus 7 indicates we have a vertical change up 7 units. Now, again, that's familiar because we were talking about these kinds of questions earlier in this module. So what I want you to recognize, though, is that base function doesn't have to be y equals x squared. Maybe that base function instead is the square root of x. So if I wanted to make the same change with this square root function, if I wanted to move it up 7 units, I would do the same exact process. I would say, let's preserve that f of x, or let's preserve that original function, and add 7 after the fact. So both of these would indicate changes from their original state and shift them 7 units upwards. So quick recap there of these vertical changes that we've already explored. The second change we explore is a horizontal change, and that change is indicated when we see y equals f at x plus h. What I want you to note here is the difference between the first two examples we're giving you. F of x plus k means you leave f of x alone and then you add something after the fact. When we explore f of x plus h, that x plus h is inside brackets. So what I would like for you to recognize is that this is a change in x. This isn't something that we are tacking on the end of the function. This is actually changing how x behaves. So if we were to give you similar examples to our last question, if we had, let's say, y equals x squared, and instead of x squared, we changed that x and we said, let's make that x minus 5 all squared. So I didn't subtract 5 after the fact. I actually changed my x value and shifted that x value by 5 units. So what we can recall from horizontal changes is that they are backwards logically. So if I go from x squared to x minus 5 all squared, what I've done is I've made a horizontal shift 5 units to the right. So we know this is horizontal, and we know this is 5 units to the right. If I wanted to do the same type of transformation with a different common function, so let's even try y equals the absolute value of x. If that was the common function I started with and I wanted to transform it, I could say y equals the absolute value of x minus 5 is the transformed version of that function shifted 5 units to the right as well. So once again, I'm not subtracting 5 after this absolute value symbol. I am manipulating the x variable. So a change in x is always going to be a horizontal change. We have 3 other transformations that we want to explore, and the first 2 of 3 are going to be reflections. So we have to pay attention to where negative signs have been placed. So our third transformation in sequence here today says if you have y equals negative f of x, so if you compare something like y equals we can use an absolute value again. If you have y equals the absolute value of x, and it now becomes or is transformed to y equals negative the absolute value of x, that's a reflection across the x-axis. So if I were to sketch those right underneath here for you, absolute value of x is just that V-shaped graph. If we have negative the absolute value of x, it's a V-shaped graph, but it opens downwards. So in this case, the vertex maintains its position because I haven't made any other kinds of changes, but we have made an imprint on the opposite side of x. What we would notice in the table of values is that all of our positive y's are now negative y values. So when we talk about reflections, we don't only need to know what it looks like or how the graph will behave differently. We also need to be very clear about which axis we are reflecting across. Now, the one significant change when we analyze these two functions would be something like the range. I know that the domain of both of these functions is the same. It stretches or reaches from negative to positive infinity in both cases for this graph. But what changes is the range, because we have to think about range as lowest y value to highest y value. So the origin is the lowest y value for the absolute value of x. So we say the range is from 0 to infinity. But we flip that range when we reflect it across the x-axis. So if I go from low to high, the negative of absolute value of x is going to have a range that starts at negative infinity because we start on the ground, or, digging down. So negative infinity is the lowest point on the graph. 0 is actually the highest point on this graph. So when we make transformations, other things or characteristics of our graphs start to be modified as well. The second type of reflection, as you may recall, introduces a negative sign in front of the x value instead of in front of the entire function. So if we were to give you, let's say, y equals the square root of x, and then we transform it and say, now let's look at the graph or explore the graph of y equals square root of negative x. If we were to draw those functions, we have sort of the eyebrow shape, if you remember that common function for the square root of x. Now, if I were to analyze this function, I would say the domain of this function is actually from 0 to infinity, because I know I start at the origin and my x value stretch to the right forever. The range of this function, so think low to high, the lowest y value is also at the origin, so it has a y value of 0, and that tail of the graph, when we trace it from left to right, is going to sneak towards the sky. So we know that our upper boundary of our range is going to be positive infinity. If we reflect this graph by introducing a negative in front of the x instead of in front of the square root symbol, what we're doing is we're creating a reflection across the y-axis instead. So if I can imagine creating an imprint across the opposite side of that y-axis, this is what my graph will now look like. It's not going to change the position of our originating or end point, but it does start to change things like the domain and the range. My domain is going to start now at negative infinity because I know that this left tail stretches towards the left indefinitely. So we start with our domain at negative infinity and we end at 0 because I could trace my graph from x equals negative infinity essentially to 0 and continuously be tracing points on the graph. The range of this function, if we think low to high, this origin point is my lowest point on the graph, so it has a y value of 0, and that left tail actually sneaks towards the sky. So we go from 0 to positive infinity as our range values. So when we deal with reflections, what I was trying to show in these last two examples is not only do you have to be very mindful of which axis we are reflecting across, you also need to be mindful that those kinds of changes can impact things like domain and range. The last type of change we want to explore or make sure we recall properly is a vertical stretch or shrink. So this is the introduction of an a value that we multiply your entire function by. So if I were to use, let's say, quadratic function this time, so we'll say x squared, and we transform y equals x squared, so maybe it's y equals 5x squared. That introduction of an a value where we multiply your original function creates a vertical stretch or shrink. What we want you to note with a vertical stretch or shrink is that the sign of that number doesn't impact how wide or how narrow your graph is. It's essentially the absolute value of a that we're most concerned with. So in this particular case, because my a value is something greater than 1, I know this provides what we call a vertical stretch. And we know what factor it's by. This is a vertical stretch by a factor of 5. So if we were to graph these two functions side by side, and I'm going to exaggerate this just a little bit. So if you have a regular parabola, regular quadratic function, and then we compare that to y equals 5x squared, what you're going to notice is that parabola is much narrower through the center of this graph. What hasn't changed are the domain or range values, but what we recognize is those tails are far more extreme. So this stretch by a factor of 5 means those y values are 5 times higher than in their original state. Now, if we want to create a vertical shrink, just as a quick reminder, we have to choose an a value that's less than 1, or if you're thinking in absolutes, we say the absolute value of a is less than 1. So be mindful we're talking about fractions between 0 and 1, or fractions between negative 1 and 0. So we might say that if we have y equals negative 1/2 x squared, we've actually made two changes here. The negative sign indicates that there has been a reflection, but the reflection has nothing to do with a stretch or shrink. We are hyper-focused on just the value of 1/2. In this case, because we have a 1/2 as your a value, we say there has been a vertical shrink, where it has been shrunk by a factor of 1/2. If we were to graph this, what we would notice is this parabola is actually much wider than the original x squared. Now, I also threw in that reflection, so it would be upside down as well. So it would be much wider and it would open in the opposite direction here. So this might be a rough sketch of y equals negative 1/2 x squared. So what I want you to be very mindful of, though, is that the negative really just repositions our graph. It's the 1/2 that constitutes a vertical stretch or shrink, and because 1/2 is between 0 and 1, we know that this is going to be, in fact, a vertical shrink. So the graph definitely gets wider. So this next example gives us a picture, and we can tell that this is a square root function, but we don't want you to make any judgments about what that equation actually looks like. We should be able to tell with proper interpretation of notation how this graph is being manipulated. So what you see on your screen is a picture of y equals f of x. It's y equals some function f of x. What we want you to do initially is make a sketch. So the first sketch we want you to make says sketch the graph of y equals negative f of x. So let's think about what that actually means. If you incorporate a negative sign, you're talking about a reflection, and that reflection is either across the x-axis or the y-axis. In this case, we know a negative in front of f of x constitutes a reflection across the x-axis. So this is a reflection across the x-axis, and I'm going to be really explicit that that's the change we want to make here in this first example. And all I want to do now is in my mind draw what that would look like. So if I were to continue and create a mirror image on the opposite side, this would be the sketch of y equals negative f of x. So for each of these examples, we're starting with your original function, and that's the line we see in red on your screen. And we are redrawing that line to incorporate the changes that have been made to our equation. So there's part A. We have sketched y equals negative f of x. I've reset our picture, and now I'm interested in sketching y equals f at negative x. So once again, this is a reflection, but it's a reflection across the other axis. This is a reflection across your y-axis. So if you can imagine folding this graph along the y-axis, what would our resulting function look like? And you can do this very specifically. You can actually work out these points quite accurately. I'm just going to do a really rough sketch here. But if we wanted to sketch the reflection across the y-axis, I know instead of having a point at, let's say, negative 2, 0, I'm going to have that point at positive 2, 0. And this graph is going to stretch further to the right. So let's fix that here. This is going to be the sketch of y equals f at negative x. So in this particular case, we can see it's a very different graph or a very different result than our original transformation, which was of reflection across the x-axis. A reflection across y in this case is going to impact, of course, our domain of the function. So the domain is going to change. The range is not going to change from its original state, but you can see how the behavior of the graph looks very different. Our last set of transformations wants us to explore what happens with y equals f at x minus 5 plus 3. So what's happening here is we have some vertical and horizontal changes. Whenever you have vertical and horizontal changes, or let's add reflections in this mix, or stretches or shrinks, what you want to do is make note that vertical changes need to always be done last. If you don't do a vertical change last, you might be reflecting along the wrong axis, so you have to be super careful about that. In any case, x minus 5 in brackets indicates that there's been a change to our x value. We know that these kinds of horizontal changes or horizontal shifts are backwards logically. So f at x minus 5 means we're going to move our points 5 units to the right. So all of these points on the grid are going to shift themselves 5 units to the right. The plus 3 at the end of our function is a vertical change. That vertical change of plus 3 means we are going to move all of our points up by 3 units. Now, I don't necessarily want to do this point by point. I find it easier just to pick the easiest point to manipulate and work from there. So if I know that the point on my original graph has an x value of -2 and a y value of 0, all I want to do is pick up that point and move it 5 units to the right and 3 units upwards. So if we move that 5, so 1, 2, 3, 4, 5, and then 3 units upwards, 1, 2, 3. This is the new point on that graph. That's where that point has been translated to or transformed to. So what we want to do is just mimic the same shape of the graph. If you're not quite comfortable doing that, you can actually pick some other points and move them the same way. So if I know that this was an original, let's find a nice one here. This was an original point on my graph. I can still say that one is moved 5 to the right. So 1, 2, 3, 4, 5 units to the right and 3 units up. So 1, 2, 3. I know my graph is going to pass through that point as well. But I can really just draw the same shape. I know that my eyebrow shape has been maintained. Maybe I didn't increase that so well, but my eyebrow shape has been maintained. And by moving my points 5 units to the right and 3 units up, I'm giving the new location of my function. So these exercises are important for us to be able to spatially manipulate the location of these functions and have those relocations really indicative of how we changed the original function. Now, instead of working with sketches, example number 2 is very different. It says, if y equals 3 times f of x plus 6, so that's your original function, show the equation of the same function changed horizontally 7 units to the right and 5 units down. So if that were my original function, how would I move this 5 units to the right and 7 units to the right and 5 units down? We know that if we want to move something horizontally, that's a change in x. So that's the piece of the function that's going to be manipulated 7 units to the right. If we know it's 7 units to the right, that new x value is going to become x minus 7. So just keep that in mind. We don't need to make that change quite yet. Let's explore the other change to this graph. The second change says we want to move this whole thing 5 units down. And what we know is that whenever we have a function that we want to move vertically, we tack that number onto the end of the equation. So we already have a plus 6, and that's kind of insignificant. But what we want to do is manipulate this whole thing another 5 units down. So we have to subtract 5 off the end of the function in order to make that true. So if I clean this up and rewrite the function, I have y equals 3 times f of x minus 7, so that means I moved 7 units to the right. And then if we have plus 6 minus 5, that minus 5 moves us downwards. So we can actually clean this up and combine those last two constants. So instead of plus 6 minus 5, we can just say that's a positive 1 now at the end. So we've manipulated our original function and moved it 7 units right and 5 units down. Our third example says if you start with y equals p of x, so we have a new original function. And again, we'll always give you a function to start with, and it might be an actual equation or it might just be the name of a function like it is in this case. So if y equals p of x is your original function, write the new equation of the function if we reflect it across the x-axis, if we translate it horizontally 3 units to the left and 2 units upwards. So let's start with the reflection. If you reflect something across an x-axis, what you're doing is you're putting a negative in front of the whole thing. So we'll have a negative in front. Now, if we also translate this horizontally 3 units to the left, we know that's a change in our x value. 3 units left is actually going to be x plus 3. The last change we make here is a vertical change of 2 units upwards. So if we add 2 units to the end of this equation, we know we're creating that change or movement upwards. So if I were to write this equation properly now, we have y equals negative p at x plus 3, so we've got that x plus 3 in brackets, plus 2 afterwards, because we know if we add 2 afterwards, that indicates a vertical change, and in this case, that's 2 units upwards. So that's your final answer of our translated or transformed equation. With example number 4, it's a slightly different ask here. We have y equals the absolute value of 2x minus 4. And what we were being asked to do is to graph it and to analyze it. So by graphing, we mean we want you to make a sketch by hand. This is good practice. And although you're going to have your calculator for this exam, it doesn't sort of diminish the importance of being able to fill in a table of values properly. So we're going to build a table of values so that we can see some of the ordered points or ordered pairs that this graph is going to pass through. So let's draw a nice little table here. I don't get so fussy that our table has to be in order for x's, but I will suggest that you choose x's that are positive, x's that are negative, and of course an x value of 0. So you might want to choose, let's say, x equals negative 5. Maybe you want to choose x equals negative 3 or negative 2, maybe negative 1 or 0. I'm going to build this table with lots of different options. And then we're going to sort of explore the shape of the graph. So I'm going to go into the positives and say maybe x is 0, x is 1, x is 2, maybe x is 3, or x is 5. So my job now is to find the y values for each of those corresponding points. So once again, we're dealing with absolute value symbols. So if we start with, let's fix this up here. If we start with x is negative 5, then essentially the equation we're looking at is y equals the absolute value of 2 times negative 5 minus 4. So we need to work this from the inside out. 2 times negative 5 is negative 10, minus 4 is going to be negative 14. But when we take the absolute value of negative 14, remember we have to be mindful that this is not necessarily a direction, but a certain number of jumps we are away from 0. So the absolute value of negative 14 is actually positive 14. So we can put that in your table of values. That's a pretty extreme y value, so if we don't end up using it, that's okay. Next, we have an x value of negative 3. So once again, we have y equals the absolute value of 2 times negative 3 minus 4. So if we work from the inside out, 2 times negative 3 is negative 6, minus 4 is negative 10, and the absolute value of negative 10 is positive 10. So we've got positive 10 as your y value in the second coordinate. If x were to be equivalent to negative 2 now, if we keep working down the table, we get y equals the absolute value of 2 times negative 2 minus 4. So this gives us 2 times negative 2, or negative 4, minus 4 more, or negative 8. And the absolute value of negative 8, of course, is positive 8. So you can fill that in as well. This is all just scrap work that I'm showing on the side here. If we have an x value of negative 1 now, then y will equal the absolute value of 2 times negative 1 minus 4. So this becomes negative 2 minus 4, or negative 6, gives us a y value of positive 6. So we're building a nice table at this point. If x were to be 0, this is an important point for us. If x were equal to 0, y is equal to the absolute value of 2 times 0 minus 4, or the absolute value of negative 4, which we know is just positive 4. Now, if x were 1, we have y equals the absolute value of 2 times 1 minus 4. And 2 times 1 is 2. 2 minus 4 is going to be negative 2. So the absolute value, of negative 2 is going to be positive 2. We're starting to get a nice looking table here. So let's keep going. If x were equal to positive 2, then we have y equals absolute value of 2 times 2 minus 4. Essentially, 4 minus 4 is 0, and the absolute value of 0 is also 0. That's significant because that's an x-intercept. So if we choose x equals 3, then we have y equals absolute value of 2 times 3 minus 4. So y will equal 6 minus 4 inside is 2. Absolute value of 2, of course, is positive 2. Now, last one we have here on our table, if x is equal to 5, let's fix that here, then y will equal absolute value of 2 times 5 minus 4. 2 times 5 is 10. 10 minus 4 is 6. So y is equal to the absolute value of 6, or we know just 6. That's a ton of points for us to be plotting on this graph now. So let's start to put them on paper and see how this shape is evolving. When you're ready to build your graph, make sure you clearly label your axes and include a scale. So when I plot these points, I can start with -3, +10. I didn't go much higher than +10 for a y value, so I'm going to omit the first point that's on the table. But when x is -3, y is +10, so we know we're sitting at this location. Now we can plot our second point of -2, +8. So when x is -2, y is 8. So we're passing through this point here. Our next point is -1, +6. So again, x is -1, y is +6. Then we have the point 0,4, which is significant because that is an intercept. We have a y-intercept at that location. So I'm just exaggerating these points so you can see them a little bit better. When x is 1, y is 2. When x is 2, our y value is 0. So that's significant because we have an x-intercept at that location. And then our graph starts moving upwards again. So when x is 3, y is 2. And when x is 5, so we've got 1, 2, 3, 4, 5, my y value is +6. So we've got this point labeled right here. So if we know this is to be a V-shaped graph, we have a really good indication of how our graph is behaving. If you'd like, you could pick a couple more values to the right of the points that we've already found, and you would see the trend holding. So what I want you to recognize, though, is with a V-shaped graph, we should be connecting these dots with a ruler. If it's a parabola or some sort of root function, we don't want to be using a ruler because those are curved lines. Here, we know that these are perfectly straight lines, and we can use a ruler to connect the dots. So we've got one end of our V-shape hitting, going through those points, and we've got a second branch of our V-shape holding or going through these points, and we want to make sure you extend the tails of your graph to the edges of your grid space. So this would be a good picture for y equals the absolute value of 2x minus 4. When we analyze a function on your test, I'm going to be very particular about the pieces of information I want. So oftentimes, analysis for a graph are going to include things like the domain of the function, the range of the function. We're going to be asking for the intercepts, but specifically we'll say what is the x-intercept, what is the y-intercept. We also want to talk about where the graph might be positive or negative. So where is this graph sitting above the x-axis, and where is this graph sitting below the x-axis, or where is it negative? Aside from that, we might ask you if there's a maximum point or if there's a minimum point. So let's go ahead and analyze these parts of the function. So if we want the domain of the function, we have to imagine if we're tracing our graph from left to right, which x values are the lowest and which x values are the highest. So I can see that the tails of the graph stretch in both directions and there are no gaps in this graph. So the domain of this function goes from -infinity to +infinity, or we can say XER. X is an element to the real numbers. The range of the function is low to high, so I want to highlight that vertex as my low point. That's the low point on the graph, but range is always written in terms of y values. So we say the range of this function starts with a y value of 0 and increases to positive infinity because we can see the tails of these graphs stretching towards the sky. Now there is one x-intercept that we found, and it was an ordered pair 2, 0, so we can just document that as your x-intercept. The y-intercept of this function is where the graph crosses the y-axis, and that's happening at 0, positive 4. We already found that point as well. The next two are kind of interesting because we're saying where is the graph positive or sitting above the x-axis, and where is the graph negative or sitting below the x-axis. For positive parts of the graph, I'm talking about basically everything here that's sitting above that x-axis. But there's a problem. I can't just say this graph is positive everywhere, because when I hit that vertex, I'm not positive or negative at that point. I'm actually in transition. So this graph will be positive from negative infinity until we hit that x value of 2. And at x equals 2, we're actually on the x-axis. We're not completely above it. So that's the first branch of the graph that's positive. And then we continue being positive on the other side of 2. So we say from 2 to infinity. So those two branches of the graph are sitting above the x-axis, but we're not allowed to include x equals 2 because at that point we're in transition. We're actually sitting on the x-axis. So the next piece of analysis here is asking where this graph is negative. So we're saying which branches of the graph are sitting below the x-axis. Well, there aren't any branches that are sitting below, so we say there are none. Please make sure that in questions like this, if we're asking you where the graph is, say, negative and it doesn't exist as a negative interval, what you need to do is make sure you're explicit and say there's none or it's not applicable. If you leave it blank, we're not really sure if you understand the question that's being asked. Now, aside from that, we have maximum or minimum values. A maximum is a high point and a minimum is a low point. There's no real high point because the tails of the graph sneak towards the sky forever. So we say there's no real maximum. But in terms of a minimum, we have an absolute minimum at the coordinate 2, 0. We say it's an absolute minimum because it is absolutely the lowest point on our graph. So we've got an absolute minimum at the coordinate 2, 0. So not only were we able to sketch this graph by hand and build a table of values, we were then able to analyze this function completely. Now we want to do the same activity with example number 5. We're given a new function this time, y equals negative absolute value of x minus 3 plus 4. So we know that an absolute value function, if it has an x inside those absolute value symbols, is going to be a V-shaped graph. Sometimes I encourage students to take a look at the transformation so you have a really good idea of how this graph has changed. So we know the original function is a V-shaped graph that opens upwards, but we've made some modifications here. The -1 means that we have reflected this graph across the x-axis. So instead of this V-shaped graph opening upwards, it's now opening downwards. But we also made a couple of other changes. This x minus 3 inside those absolute value symbols means we've actually moved your original vertex from 0, 0, 3 units to the right. So we've moved right by 3 units. The last change we've made is we've moved this whole graph up by 4 units because we're seeing a +4 on the end of the function. Sometimes what that does is it allows you to find sort of one of the most important pieces of your graph or the vertex of this type of function. So if I can imagine my vertex used to be at 0, 0, but I move that vertex 3 units to the right and 4 units up, I know that the point 3, 4 is going to be a critical point on my graph. If I know that these functions are symmetric, so these V-shaped graphs are sort of even on both sides, what I can do is use 3, 4 as the central tenant in my table of values. So when I pick my values for x, yes, I could randomly choose whatever I want for x and solve for y. But if you know that that vertex is sitting at the ordered pair 3, 4, put that in the middle of your table and then pick values to the left of that and values to the right of that. So I'm going to pick maybe x equals 2, x equals 1, x equals 0. We're going to pick a few more, or a few extras. And maybe we'll pick x equals 4, x equals 5, and x equals 6. So I'm looking at both sides or beyond both sides of that vertex so that we can get a really good picture of how this graph behaves. So if you didn't want to use this method, you could pick your own x values and solve for y, as we did in the previous example. But if you know where that vertex is repositioned, you can use that to your advantage and build a table of values that is perfectly symmetric. So let's start again with our scrap work. If x is 0, we know that y will equal negative the absolute value of 0 minus 3 plus 4. So 0 minus 3 is negative 3, but be careful here. If I take the absolute value of negative 3, it's positive 3. This is what we cannot do here is make two negatives a positive. That's not allowed across an absolute value symbol. So the negative on the outside needs to stay, but we have to evaluate the absolute value of negative 3, which we know to be just 3. These can be tricky, so make sure you're careful when you work out these values on your table. Negative 3 plus 4 is positive 1, so when x is 0, y is 1. Now, if we have an x value of 1, then we get y equals negative absolute value of 1 minus 3, all plus 4. So y will equal negative, now 1 minus 3 is negative 2, but the absolute value of negative 2 is just positive 2. Once again, we cannot say that two negatives make a positive when those two negatives are on opposite sides of an absolute value symbol. So negative 2 plus 4 is positive 2. So we've got another value on your table. And we can keep going from here. So if x is equal to positive 2, then we have y equals negative absolute value of 2 minus 3, all plus 4. So this is going to be negative absolute value of negative 1 plus 4. And again, two negatives don't make a positive. We have to leave that negative on the outside and work at negative 1 on the inside. So absolute value of negative 1 is only positive 1. And if we add 4, we get positive 3. So we're building quite the table of values here. If we have for our next value x equals 4, then y will equal negative absolute value of 4 minus 3 plus 4. So y will equal negative absolute value of 1, which we know is just 1 plus 4, or 3. Next, if x is equal to positive 5, then we have y equals negative absolute value of 5 minus 3 plus 4. So this becomes negative absolute value of 5 minus 3. Well, 5 minus 3 is 2, so absolute value of 2, of course, is 2. Negative 2 plus 4 is positive 2. We've got one more value on our table, so if x is positive 6, then y equals negative absolute value of 6 minus 3 plus 4. So y will equal negative 3 plus 4, or positive 1. So once again, we found enough points for us to be comfortable making a sketch. If you wanted to pick x values that are further into the negatives, just to be certain or just to be sure, you're welcome to do that as well. So I'm going to go ahead and plot these points. When x is 0, my y value is 1. When x is 1, my y value is 2. When x is 2, my y value is 3. We know we pass through 3, 4. Then we've got 4, 3, 5, 2, and 6, 1. So we can definitely see a beautiful pattern emerging here, and it makes it nice and easy for us to graph these functions. Now, typically when you find intercepts, you'd like to find them and make sure they're both on the table of values, but we can be very certain that we're finding the proper intercepts by looking at our graph in this stage. So the only other thing we want to be doing here is analyzing the function. So let's go back and think about those points of analysis. I'm just going to get rid of our scrap work so we have some space to do this right below the graph. So for analysis, again, we want domain, we want range, we want x-intercepts, we'll ask for y-intercepts, we'll say where's the graph positive, where's the graph negative, and do we have a maximum or do we have a minimum? So high points and low points. If we start with domain, we know that the domain of this function stretches from the left to the right indefinitely. So the domain is going to be from negative infinity to positive infinity, and those are all the x values that are covered. Range is low to high, so my lowest y value is going to be negative infinity, but my highest y value is going to sit at that vertex. So at that vertex, we know the y value is positive 4. So my range has to go from negative infinity to positive 4. And if it helps for you to put that coordinate here, just to label it, you're welcome to do so. Now for x-intercepts, we see there is an x-intercept at negative 1, 0, and there's a second x-intercept if we count it out. 1, 2, 3, 4, 5, 6 at 7 zeros. So 7 zeros is the location of your second x-intercept, and we've documented those as ordered pairs. We have a y-intercept, or we're crossing the y-axis at the coordinate 0, 1. We can see that again very clearly on our graph. And now we want to entertain where this graph is positive or negative. If I were to highlight the segments of the graph that are above the x-axis, those purple highlights are going to be positive. So we say that chunk of the graph is above the x-axis between x equals negative 1 until we hit that other intercept at positive 7. So we're saying between negative 1 and positive 7 for x values, the graph is sitting above the x-axis. If we want to find the negative parts in the graph, those are the, let's say, the green segments of this graph. The green segments are going to start and stop in very different parts or in very different ways. This graph is negative or below the x-axis from x equals negative infinity, which means as far left as you can imagine, until we hit that x-intercept. So until we hit x equals negative 1. So between x equals negative infinity and x equals negative 1, which would be the left side of this graph, the graph is sitting below the x-axis. We also have a second portion, so we have to use that little union or together with. That starts, if I trace with my pencil, oopsie, let's get rid of that. If I trace with my pencil, as soon as x equals positive 7, or is beyond positive 7, we're back below the x-axis. So this graph is negative from 7 to infinity. And it doesn't mean that infinity as in high towards the sky. We mean infinity as far right as you could imagine. So remember, along the x-axis, infinity is to the right, negative infinity is to the left. So for maximum and minimum values, we have an absolute maximum or an absolute highest point on the graph at that coordinate of the vertex, so 3, 4. And for a minimum or a low point, we say there's none. I can't pick a low point on this graph because the tails of the graph get lower and lower the further we trace. So we've been able to sketch these graphs by hand and analyze them. Now it's your turn to do some of the homework. So please have a look at the homework questions from 9.8. And as always, if you have any questions as you go, please don't hesitate to reach out. This is now the end of this module, so you can start your preparation for the module test. We will not be covering regression in this course, so you can omit the exercises and content from 9.9.